From what you've already read in your course book, you should know how wheel alignment affects tire life, steering, handling, and traction. Proper wheel alignment is absolutely essential for maximum tire life, for steering stability at all speeds, for normal steering effort and return after turning, for proper tracking and cornering, and even ride smoothness and stable braking.
Anytime a vehicle is in for service, take a few minutes to look for obvious signs of misalignment. And if you find evidence of misalignment, be sure to inform the service advisor. Many times a customer will ask for an alignment because they're experiencing some kind of steering, handling, or ride control problem. Or maybe they've noticed that their tires have been wearing rapidly or unevenly. Then again, they may have some other type of drivability problem that is not alignment related, but they think it is. Dealership service advisors play an important role in your alignment process because they have direct contact with customers. Service advisors start by interviewing customers to find out why they want to check the alignment on their vehicle. They should find out as much information as possible about the exact nature of their problem. When did the problem first start? Does it do it all the time? If not, under what conditions does the problem occur? The customer should be asked to describe their problem as best they can. Their use of descriptive terms may not be the same as your definition of certain words. So if the customer says they're experiencing a vibration or shimmy or pull, make sure you understand their meaning so you're on the same wavelength. It's also important to ask the customer about how they use their vehicle. Do they regularly haul heavy loads such as sample products in the trunk or several people in a carpool? Do they do most of their driving at highway speeds or around town?
Loading and speeds can have a bearing on tire wear, as well as how a vehicle steers, rides, and handles. So consider all the facts before jumping to any conclusions.
Test driving the vehicle serves two important purposes. It allows you to confirm the condition described by the customer, and it gives you a hands-on feel for how the vehicle steers, handles, and rides. You should lay out a standard test drive route that you use every time. That way, you'll be able to anticipate how the vehicle will perform on any part of the route. The test drive should duplicate the normal driving conditions of the vehicle. If the customer says they do the majority of their driving on the highway, the test drive should include an open stretch of highway so you can get a feel for steering stability and check for pull to either side. If the customer says most of their driving is around town, the test drive should do the same and include a number of 90-degree left and right-hand turns.
There are a number of things you should pay particular attention to while test driving a vehicle. You can make a mental note of these things or jot them down as you drive.
First, notice how much effort it takes to steer the vehicle, particularly while maneuvering and turning at low speed. Does the amount of effort feel normal? Does it feel the same when turning in both directions? Does the steering wheel return to its center position smoothly and easily after completing a turn? Also, note any excessive body sway or leaning when cornering at normal speeds. This could indicate a sway bar problem or worn shocks or struts. Roll down the window so you can listen for tire squeal or any unusual noises while turning. Tire squeal could indicate misalignment as well as worn or bent steering components. Make a couple of quick stops, not a panic stop, but a faster than normal stop to see if there's any evidence of brake pull to either side. Any shudder or vibration that is felt when braking would indicate a brake problem, not a steering or alignment problem. Don't forget that some noise and pedal feedback is normal if you stop hard enough to engage the anti-lock brake system. Also, pay attention to how the suspension reacts to the sudden change in momentum. If the nose dives sharply, the shocks or struts may be weak. On a straight stretch of level road, check for any tendency to pull or lead to either side. Is the steering wheel centered or is it cocked to one side? Remember that a heavily crowned road surface will make a vehicle lead to the outside. Does the vehicle feel in control? Any looseness in the steering wheel or wander from side to side while driving straight could indicate worn steering or suspension parts that may need to be replaced. Play in the steering wheel should be less than half an inch. At highway speed, feel for any vibration or nibble in the steering wheel as well as the vehicle itself. A rapid side-to-side nibble typically indicates a wheel with a dynamic imbalance problem, excessive lateral runout, or a bent rim.
A more forceful vibration or wheel tramp could indicate a wheel and tire with a static imbalance, an out-of-round wheel or tire, or excessive runout in a wheel, tire, or hub. All these conditions can be checked later during the vehicle inspection. Vibrations that increase with speed usually indicate an out-of-balance condition in a tire and wheel assembly, but can sometimes be caused by driveline misalignment or a rear-wheel drive shaft that's out of balance. High-speed wheel shimmy could indicate a combination of imbalance and worn suspension components. Note too the amount of feedback through the steering wheel. Some vehicles tend to give much more road feel than others, but unusual steering harshness could also indicate worn or loose parts.
Your test drive should also include a short stretch of rough pavement to see how the suspension handles bumps and dips. Does the ride feel unusually bouncy, or does the suspension bottom out? Either condition could indicate weak springs or worn dampers. Does the vehicle steer straight, or does the steering jerk to either side when hitting bumps?
Any sudden change in directional stability could indicate a bump steer condition caused by misaligned or worn steering parts.
Roll down the window again and listen for any unusual suspension noises. Clunks or rattles may indicate worn or loose components.
At the conclusion of your test drive, you might want to do a simple bounce test to confirm your suspicions if the shocks or struts felt weak when driving over bumps.
The inspection of the vehicle itself should always begin by checking the tires. The things you want to pay close attention to are inflation pressure, tire sizes, and the condition of the treads. Inflation pressure has become a more important issue due to the extended service intervals provided by the flexible service system. The customer should be made aware that accelerated tire wear is caused by underinflated tires. The customer should have tire pressures checked between visits to your dealership. The recommended tire inflation pressure can be found on a decal on the inside of the fuel filler door. The recommendations on the decal are for best ride, traction, and all-round driving performance.
Front and rear tire pressures often differ and may also vary according to load or driving conditions. So make sure you use the correct reference numbers. Higher than normal loads, for example, typically require additional pressure in the tires.
Do not use the pressure rating number on the side of the tires. This number is a maximum inflation pressure specified by the tire manufacturer that is not to be exceeded under any circumstances. Inflation pressure must be checked when the tires have cooled down to normal room temperature, not right after driving, because warm tires will read higher than normal pressure. Next, check the tire size of all 4 tires to confirm they're the correct size. Once you've checked tire pressure and size, examine the condition of each tire. If the tread wear indicators are showing, the tires are worn and should be replaced. Generally speaking, a tread depth of less than 3 millimeters is unsafe. Check each tire for any foreign objects such as nails, damage to the tread or sidewalls, or separation of tread from the tire carcass. Pay close attention to the condition of the tread and note any unusual or uneven wear that would indicate misalignment or suspension problems. Here are some examples. Heavy wear on the outside edges of a tire can be the result of hard driving and cornering at higher than normal speeds, but it may also be the result of chronic underinflation. You might want to check the tire and wheel for a leak. Heavy wear in just the center portion of the tread usually means the tire has been overinflated. Check air pressure and vent air as needed to restore proper inflation pressure.
Also, you should advise your customer about the importance of following the recommended inflation pressure on the decal in his vehicle.
Heavy wear on one side only usually indicates improper camber or toe alignment. This may be the result of worn or bent steering or suspension components. Improper toe alignment can also cause a feathered or sawtooth wear pattern across the tread. You can feel this condition by running your hand across the tread. If it feels smooth one way but rough the other, toe correction is needed. Bold spots or scalloped wear on the tread may result from an imbalanced tire and wheel assembly, a tire defect, or possibly worn suspension components such as shocks or struts. It's also important not to overlook the wheels when you're inspecting the tires. Check for dangerous conditions such as cracks or impact damage. Rim damage or scuff marks may be the result of impacts with curbs or potholes. If you noticed any vibrations while test driving the vehicle, such damage may indicate a bent rim. Wheel and tire runout can be checked with a dial indicator if you suspect a problem. A wheel or tire with excessive runout can cause a vibration. Always refer to the Mercedes-Benz specifications in WIS for the maximum amount of radial and lateral runout that is acceptable. After checking the tires and wheels, measure ride height. This check must not be overlooked because ride height establishes the basic positioning of the suspension and steering. Mercedes-Benz uses a process that measures the angles of the front lower control arms and the inclination of the rear axle to determine ride height. We'll describe this process in detail in the next video section. Keep in mind that vehicle overloading will affect the ride height measurement. Refer to the requirements for vehicle load prior to taking a height measurement. If ride height is below specifications, it can be corrected by installing new springs or, in some cases, thicker rubber spring pads. Vehicles with any form of automatic leveling system would require adjustment as explained in WIS. You should also give the vehicle a quick examination for any evidence of structural damage or recent collision repairs. Such conditions as sag or twist may be present in the body or frame that affect ride height as well as wheel alignment.
Let's move along to the steering linkage. One way to check for looseness in the steering linkage is to do a dry park check.
With the full weight of the vehicle on the wheels, have a helper rock the steering back and forth while you check for looseness. There should be no visible movement in steering couplings, tie rod ends, or other steering links. Idler arms may show some movement but should be tested by applying a specific load vertically to the arm. Check WIS for additional information about idler arms. Check the rack and pinion steering linkage. Squeeze the rack bellows to feel for any looseness in the inner tie rod socket assemblies while the steering is being rocked back and forth. Note the condition of the bellows and for signs of fluid leaks. Looseness between the pinion and rack will show up as play in the steering wheel. This may indicate a faulty free play self-adjuster or excessive wear.
On vehicles with McPherson struts, don't forget to check the upper strut mounts while the weight of the vehicle is on the wheels. The strut bearing assemblies support the weight of the vehicle and serve as the upper steering pivots.
If you see any looseness or wobble in the upper mounts as the steering is rocked back and forth, the upper bearing assemblies may be worn. Problems here can affect steering stability, steering effort, and steering return. Wheel bearings must also be checked with the wheels off the ground. First, spin each wheel by hand. Be sure to check all 4 wheels, not just the ones up front. Any rumbling, clicking, or growling noise or roughness may indicate worn or damaged bearings. Some light scraping noise is normal and is caused by the rotor rubbing against the brake linings. Spinning each wheel by hand should also reveal any abnormal brake drag. It's a good idea to apply the brakes and then release the pedal to see if the pads retract. If a brake hangs up, further diagnosis will be required. Next, grasp the wheel at the top and bottom and try to rock it back and forth. Excessive play may indicate misadjusted or worn wheel bearings. Refer to WIS for the maximum play allowed. If the wheel bearings only require adjustment, inspect the condition of the bearing grease while making the adjustment. Replace the grease as necessary. If damage to the bearings or races is suspected, remove and inspect them, and replace them if required. Use the factory recommended wheel bearing grease and adjust bearing play to specifications. Continue your undercar inspection by checking the control arm bushings, front and rear, as well as the sway bar bushings and links. Cracked, deformed, or crushed bushings should be replaced. When inspecting coil springs, front and rear, check for breakage, physical damage such as nicks or gouges on the painted spring surfaces, which may lead to future breakage, proper alignment between the ends of the springs and their pads, and any evidence of bottoming or contact between coils. When weak or damaged springs are replaced, it's required that both springs on an axle be replaced in order to maintain equal height from side to side and to provide a balanced ride and proper handling. On vehicles with torsion bars, make sure both ends of the torsion bars are properly supported.
Shock absorbers should be inspected for fluid leakage as well as loose, deteriorated, or broken mounts. The presence of some dampness in the vicinity of the seal is normal. But if the dampness extends more than a few inches down the body of the shock, the seal is leaking and the shock should be replaced. Check all 4 shocks so you can make the best recommendation to the customer.
The same checks also apply to struts. Oil leakage from the strut housing would be grounds for replacement. Also check for physical damage to the strut and the upper strut mounts. Boot damage usually leads to rapid joint failure, so check the condition of each of the boots around the constant velocity joints. The boots keep grease in and contaminants out. Any boots that are cracked, torn, or loose should be repaired immediately. Before taking any alignment measurements, the vehicle riding height must be within specifications. The electronic level gauge, or ELG, is a precision instrument used for this procedure. The tool consists of a computer and an inclinometer. The electronic data transfer and charging station made by Romes conveniently connects the ELG to the alignment console. Models equipped with a self-leveling suspension should be fully raised, then fully lowered before ride height is measured. Install the inclinometer on the front lower control arm. An adapter plate is required on the M-Class. Press the Save button on the computer, then move the inclinometer to the other control arm and save that value. Locate the measuring point on the rear axle shaft and hold the inclinometer first onto the left rear axle shaft, then the right axle shaft to measure the rear axle angle. With all the values saved, you can now transfer the data to the alignment console, which will evaluate them against specifications.
In this segment, we'll look at the basic alignment angles, which are the essence of what wheel alignment is all about. Understanding the role that each angle plays in the steering and suspension will allow you to diagnose and correct alignment problems on virtually any vehicle. Let's look at toe. The toe angle refers to the parallelism between the wheels on the front or rear axle. Toe may be specified in inches, millimeters, or degrees. When the leading edges of the tires are closer together than the trailing edges, the wheels are said to be toed in. Toe in is also known as positive toe. And when the trailing edges are closer together than the leading edges, the wheels are said to be toed out. Toe out is also known as negative toe. Of all the alignment angles, toe has the greatest effect on tire wear. When the wheels are perfectly parallel to one another, a condition called zero toe exists. Here, the tires experience the least amount of rolling resistance and scuffing. This maximizes tread life as well as fuel economy. If the wheels are driven in a toed in or toed out condition, the tires will scuff as they roll. Toe out misalignment will cause the inside shoulders of both front tires to wear rapidly. A directional feathered wear pattern may also develop across the face of the tread, which can be felt by running your hand sideways both ways across the tread. The tread will feel rough when going from the outside toward the inside. Toe-in misalignment, which is less common, will cause the outside shoulders of both front tires to wear rapidly. The same type of directional feathered wear pattern may also be present on the tread, but the pattern will point toward the inside rather than outside of the tire. To minimize tire wear, toe needs to be as close to zero as possible while the vehicle is traveling down the road. But to achieve this condition, toe must be adjusted to compensate for suspension compliance. Most suspension bushings are designed to give a little underload to help cushion and dampen road shock. This reduces steering harshness and noise, but the drawback is that it also allows subtle changes in toe alignment. On rear-wheel drive vehicles, the front wheels tend to toe out slightly as they are pushed down the road. Consequently, vehicle manufacturers typically specify a small amount of static toe in when the vehicles are aligned to compensate for suspension compliance. Toe changes slightly as the suspension moves up and down, The design of a short arm, long arm suspension helps to offset toe change somewhat by changing camber at the same time. As long as the toe and camber changes are the same on both sides, directional stability is unaffected. But if the steering rack or linkage is not parallel to the ground, unequal toe changes can occur as the suspension travels through jounce and rebound. This can cause a condition known as bump steer or toe curve, where the vehicle suddenly veers or jerks to one side after encountering a bump or dip in the road. Steering the wheels also changes toe. The next angle we're going to examine, therefore, is the turning angle, which is also called toe out on turns. When a vehicle turns a corner, the outside wheel follows a path along a larger diameter circle than the inner wheel. To minimize tire scuffing, the toe angle must be changed so each tire can follow its own path. This is made possible by the design angle of the steering arms and is called Ackerman angle. As the wheels are turned, the inside wheel is turned at a slightly sharper angle than the outer wheel. The difference is only a couple of degrees, but it's enough to minimize tire scuffing. The turning angle is measured on alignment equipment by turning the wheels a specified number of degrees one way, then the other way. The change in the toe angle, which should be the same in both directions, defines the turning angle.
Now let's turn to the next alignment angle, camber. Camber is the inward or outward tilt of the wheels as viewed from the front or rear of the vehicle. An inward tilt is called negative camber. An outward tilt is called positive camber. The camber angle is specified in degrees. A camber specification is listed on the front and rear wheels on Mercedes-Benz models with independent rear suspensions.
Camber is not a static angle because it changes as the suspension moves up and down. When the wheels are straight up and down, the tread is in full contact with the road and provides maximum traction. Camber is a directional angle because it affects the steering of the vehicle. A wheel wants to roll towards the direction it is leaning, just like a bicycle tire. So if a vehicle's wheels are not straight or perpendicular to the road, the steering may pull to one side or the other. As a rule, the vehicle will lead or pull to the side with the most positive camber.
The effect of a camber pull is most noticeable when driving on a straight, level road. The vehicle will lead towards the side with the most camber, forcing the driver to constantly correct to the opposite side to keep the vehicle traveling in a straight line.
Camber also affects tire wear. Too much camber one way or the other loads the tire unevenly. This causes the tread to wear more on one shoulder than the other. Wear on the inside shoulder of the tire only would result from a negative camber condition, while wear on the outside shoulder only would indicate a positive camber condition. Camber wear may be caused by worn or collapsed control arm bushings, a bent spindle, a bent strut, or a mislocated strut tower, engine cradle, or cross member. Ride height also has a very important bearing on camber. Weak, sagging springs can create adverse changes in camber, as well as create cross-camber problems if the chassis leans to one side. A lower than normal ride height also forces the suspension to work outside its normal range of travel, which can create greater than normal camber changes. This can have an adverse effect on tire wear as well as handling, and should be corrected by restoring the vehicle to its specified ride height. In this part, we'll look at the remaining alignment angles, starting with caster. Caster is the tilt of the steering axis of the front wheels as viewed from the side. A forward tilt of the steering axis is called negative caster, while a rearward tilt is called positive caster. Caster is specified in degrees.
One of the things that caster affects is handling stability at high speed. Tilting the steering axis rearward has a stabilizing effect on the steering. The greater the tilt, or the more positive the caster angle, the more secure the vehicle feels at high speed.
This happens because tilting the steering axis changes the angle of the spindles when the wheels are steered to either side. As long as the wheels are steered ahead, the spindles remain in the same plane of travel. But as the wheels are turned to either side, the caster angle causes one spindle to move down while the other moves up. The spindle that moves down lifts the vehicle, so the weight of the vehicle resists the steering effort and tends to keep the wheels centered. High positive caster settings are often used on European luxury sedans to achieve extremely stable steering at high speed.
Positive caster has a beneficial effect up to a certain point on steering stability. But increasing caster also increases steering effort. Another consequence of increasing caster is that it also increases road feel and steering harshness. Too much positive caster may make the steering feel unusually hard and jerky, especially on rough roads. Too little caster, on the other hand, may interfere with proper steering return and may even allow wheel shimmy to occur at highway speeds. Casters should therefore be kept within Mercedes-Benz specifications for best steering performance and handling. Caster has an effect on directional stability much the same as camber does.
If there's too much of a difference in cross caster side to side, the vehicle will lead in one direction or the other. With caster, the vehicle will lead towards the side with the least amount of caster, or to the negative side. Caster lead occurs because caster changes the camber angle when the wheels are steered. Caster does not affect tire wear directly, but it can be a factor in tire wear because of something called camber roll that occurs when the wheels are steered. As we said, caster causes the spindles to move in an arc rather than in a flat plane when the wheels are steered.
Turning the wheels to either side will change the angle of the spindles, which in turn changes the tilt of the wheels. This causes the inside wheel to lean out and the outside wheel to lean in. Leaning the tires into a turn improves traction and handling as well as steering return.
But it can also increase shoulder wear on the tires at extreme angles. For this reason, vehicles with high caster angles typically experience more shoulder wear on their front tires than those with lower caster angles. High caster angles indirectly cause a camber change during turning, which will result in tire wear. This is normal and does not indicate a condition that needs to be corrected. But changes in caster due to other factors, such as worn or bent suspension components, should be diagnosed and repaired. This type of wear, which is usually associated with camber misalignment, may in fact be due to excessive caster. If caster is out of specifications or cannot be corrected using the factory adjustments provided, worn or bent suspension parts may be responsible for the condition. Caster problems can be caused by worn or collapsed control arm bushings, a bent spindle, a bent strut, or a mislocated strut tower or engine cradle or cross member.
The steering angle inclination, or SAI angle as it is known, is an imaginary line that runs between the upper and lower steering pivots. The SAI angle is the angle between this line and one perpendicular to the road.
On a short arm, long arm suspension, the SAI angle is the line between the upper and lower ball joints. On McPherson strut suspensions, as well as modified strut suspensions, the SAI angle is a line between the lower ball joint and the upper strut mount.
SAI is primarily a diagnostic angle for troubleshooting camber problems. By comparing the SAI angle to the included angle, which is the sum of the camber and SAI angles, various conclusions can be drawn about the condition of front-end components. Bent spindles, struts, mislocated strut towers, and engine cradles and cross members are often the causes of problems here. Check WIS for specific details.
The last angle we're going to look at in this segment is the thrust angle. The angle is an imaginary line perpendicular to the rear axle that bisects the midpoint of the combined tow readings of both rear wheels. If this line coincides with the vehicle's center line, there is no thrust angle, and the rear wheels are in proper alignment. But if the line veers to either side of the center line, the vehicle will have a tracking problem, as well as a rear axle steer problem. A thrust angle to the right of center is said to be positive and will cause a steering pull to the left. A thrust angle to the left of center is said to be negative and will cause a steering pull to the right. Because this type of problem cannot be easily corrected, a thrust angle alignment may be necessary. In this type of alignment procedure, front toe is adjusted to the thrust angle rather than the vehicle center line. By now, you should have a much better appreciation for how important accurate wheel alignment is for maximizing tire life, assuring proper steering and stability and control, good handling, and safe driving. In this segment, we're going to go through a typical four-wheel alignment procedure, so you can see all of the steps that are involved. Although some of the individual steps may vary a bit depending upon vehicle application and the type of equipment you'll be using, the overall methodology is basically the same.
As we've said earlier, a short test drive will confirm the steering or handling problem and may also help you identify other problems that need attention too. Be sure the test drive includes a variety of driving situations. This should include low-speed turns in both directions, a stretch of highway driving on a straight, level road, some rough pavement, and braking and handling maneuvers so you can see for yourself how the vehicle steers, rides, and handles under various operating conditions.
Following the test drive, you should have a pretty good idea of what might be wrong with the vehicle. But don't jump to conclusions just yet. Use this information to focus your diagnostic efforts as you do the preliminary alignment inspection.
If the steering felt loose and the vehicle showed a tendency to wander, for example, you'd want to pay particular attention to the condition of the components in the steering linkage as well as the wheel bearings. If a vehicle had a noticeable pull to one side, you'd want to check for conditions that might cause rear axle or rear toe misalignment or create a cross camber or cross caster condition. A vehicle that exhibited excessive body sway, rode rough or bouncy, or rocked excessively when braking would probably lead you to pay particular attention to the condition of the shocks or struts.
But regardless of your driving impressions or what you think might be wrong with the vehicle, you should always do a thorough job of inspecting the entire steering and suspension system prior to checking wheel alignment. Skipping over items or jumping to conclusions may seem like a good way to save time, but doing so may cause you to misdiagnose alignment problems and to miss other worn or damaged parts that may also need replacing. So be diligent and do all the recommended checks to make sure you don't miss anything. Do all of the steering and suspension checks covered in the previous video segment. This includes the steering couplings, steering gear, steering linkage, tie rod ends, ball joints, control arm bushings, struts, shocks, rear suspension, and all four wheel bearings. Any parts that don't meet specifications should probably be replaced before proceeding with the alignment, because worn and damaged parts cannot hold proper alignment. Once you've taken care of the preliminaries, you're ready to proceed with the alignment check.
Mercedes-Benz has very exacting procedures for accurately aligning its vehicles. As a result, the company has worked closely with several equipment manufacturers capable of producing the high-precision alignment consoles, racks, slip plates, and associated hardware required to do the job properly. All of the equipment is interchangeable, regardless of manufacturer. That's why your dealership may have a rack from one company and an aligner console from another. For this video, we'll be demonstrating this typical alignment equipment. Different manufacturers use various components and computer systems, so you should be sure to check with the directions for the specific piece of equipment you use before proceeding. We're going to show some typical console screens using this alignment equipment. The screens aren't complete, so be sure to refer to the printed information enclosed with this video or the directions that came with the alignment equipment in your shop. The racks, in particular, are very carefully designed. They must comply with the MKS alignment system, which establishes a perfectly flat and level plane for the vehicle. All of the electronic software that measures wheel alignment angles is referenced to that flat plane. Because it is so carefully positioned, MKS racks should only be used for alignments, not for other types of service work. When an MKS-compliant rack is initially installed in the shop, it is leveled off to within 1 millimeter tolerance front to rear and side to side. However, subtle shifts in the shop floor or even the routine bumps of everyday use can cause the rack to shift from its precise position. To assure that it's within the allowable 1 millimeter tolerance, you must check the rack regularly following a special procedure. There are arms at each corner of the lift designed to hold the wheel sensors normally used for alignments. The rack alignment sequence on the console is used to test for compliance. If necessary, adjustments can be made to the height of each ramp at the ladders. Minor adjustments are also possible using these foot pads. These adjustments should only be made by the equipment manufacturer. If the rack is level but the checking procedure indicates a problem, a wheel sensor unit may be at fault. Once you're confident the rack is flat and level, pull the vehicle up onto the ramp. The tires should come to rest on the front turn plates and rear slip plates. Before proceeding, an important point must be mentioned. Previously in this video, a pneumatic jack was used to raise the vehicle after it was driven onto the alignment rack. This was done to show how to perform certain mechanical checks. In practice, the vehicle must not be lifted prior to performing the actual alignment values check. Raising the vehicle disturbs the normal driving configuration, and that must not be done or the alignment values will be inaccurate. If the vehicle was raised after driving it onto the alignment rack, it should be driven again to allow it to adjust to its normal driving configuration. Install the quick clamps onto each wheel. These locator pins are designed to pass through the holes in the wheels so the clamps lock down on the wheel hub or brake rotor. This eliminates the effects of any wheel or tire runout on the alignment. If runout exists, it should be corrected separately. Lock the quick clamps onto the tire using the arms. Once locked down, you can remove the clamping handles. Remove the retaining pins from the front turn plates and rear slip plates. Now you can install the wheel sensors onto the clamps. Level them using the bubble gauge and lock them into place. Plug the cables into the sensors and turn plates. Now you're ready to begin the alignment. Start by keying in the vehicle identification. This is critical because all of the alignment specifications are stored in the computer's memory, so you must tell the console what car you're working on. Press the pre-adjustment key. This shows the actual camber and toe measurements. If these measurements are within specification, there's no need to proceed further. If not, an alignment service is required. Then select Quick Clamp. The first procedure will measure caster, SAI, the included angle, and toe out on turns. Following the on-screen instructions, turn the wheels to the right until the indicator is at 20 degrees. Continue to steer the wheel until the right wheel indicates 0 degrees toe. Now steer the wheel left 20 degrees and continue steering it until the left wheel reaches 0 degrees toe. Now, move on to measure the toe pressed values. Install the toe pressure bar at the front of the tires and save the values. The before measurements values are now displayed on the console. These are static values that present an overview of the measurements taken so far. Then the after measurement values are displayed. Pay particular attention to the toe values. All 4 measurements must be within specifications before moving on to measure caster or camber. If necessary, adjust the toe now. After you've measured all of the angles and made the required adjustments, save all the data and print it out for reference.
Once again, make sure to check the directions for operating the specific equipment you're using before attempting to perform an alignment. If a vehicle is not experiencing any steering, handling, or tire wear problems, and the readings are within specifications, alignment corrections are probably unnecessary, and you can end the job at this point. But in some cases, the reading that falls at or near the minimum or maximum specification may not be good enough for some applications or customers, and may require realigning the wheels to the preferred settings to optimize tire wear, steering and handling performance, or to correct an existing problem. Preferred settings generally provide the best tire life and all-around steering and handling performance, but not in every instance. Some situations may call for somewhat modified settings, such as adding or subtracting camber to compensate for heavier than normal vehicle loading, or adding or subtracting caster to compensate for changes in vehicle ride height. If a reading is way out of specification, it usually means something is bent or mislocated. and that additional repairs may be needed to restore proper wheel alignment. But as long as the actual readings are not too far out of specifications, adjustments should be all that's necessary to bring the readings back to where they should be. Here's something else to remember. When camber and/or caster readings are out of specifications, you should also check SAI and included angle to determine if they're within specifications or not. If you're unable to make the necessary alignment corrections, you may suspect frame damage or bent components.
If corrections or changes in wheel alignment are needed, they should be made in the following order. Always start with ride height, then rear camber, rear toe, camber caster on one side front, then camber caster the other side front, and finally front toe.
Rear camber correction should be made first if required, because the tilt of the rear wheels not only alters rear ride height, which can affect the front caster reading, it also affects rear toe.
The camber adjustment will vary depending on model, so refer to WIS for specifications. Generally speaking, rear camber is adjusted by moving the upper control arm in or out, or by turning cam bolts. Adjust the suspension until the rear camber reading is within specifications or at the preferred setting. Repeat for the other wheel. After camber has been adjusted, rear toe can be set. Rear toe is generally adjusted by lengthening or shortening the rear links, or turning offset trailing arm bushings.
If camber cannot be brought back into specification with the limited range of factory adjustment provided, SAI and the included angle should be checked to determine if something is bent or mislocated. Toe is the last angle to be adjusted and should not be changed until all other corrections have been completed. Before this adjustment is made, make sure the steering wheel is centered. This is necessary to equalize the steering linkage on both sides for on-center steering. If the steering wheel is not centered, it may end up being off-center when driving straight. What's more, the wheels may not toe out evenly when turning, creating a tire wear condition that wasn't there before you changed the toe adjustment.
Toe is adjusted by increasing or decreasing the length of the tie rod. On rack and pinion steering systems, the outer tie rod jam nut must be loosened to turn the tie rod. On parallelogram steering systems, loosening the clamps on the tie rod sleeves allows the sleeves to be turned to change the length of the tie rods. The sleeves may have to be replaced if they are too badly corroded or are hard to turn. Toe should be set to the preferred specification to minimize rolling resistance and scuffing for maximum tire life.
When all the alignment corrections have been made and confirmed, save and print the data. The before and after alignment readings will show the corrections that were needed and made.
If possible, a final test drive should be done to make sure the changes you made corrected any problems that might have been present and to confirm the vehicle steers, rides, and handles properly. That completes the basic alignment procedure. You can see how easy alignments are with today's computerized equipment and how you can solve a wide variety of steering and handling problems with a few simple adjustments. Although not part of the suspension or steering system, the Distronic active cruise control system is dependent on both the suspension and alignment being correct to operate properly. A brief overview of the operation of the Distronic system is included here for that reason. Distronic is a unique system that detects the speed of other vehicles and traffic up ahead. When driving with the cruise control engaged, if the distance between the Mercedes-Benz and the forward vehicle decreases below a predetermined distance, the speed is automatically adjusted. This sensor, mounted behind the grille, sends out a series of radar signals. The aiming of this sensor is critical to the accuracy of the whole Distronic system. If the vehicle ride height or wheel alignment is out of specification, or if the sensor was moved during a repair or replaced with a new one, a special procedure must be followed to aim the sensor correctly. Any of the approved headlamp aimers are required for this process. This service should be performed after all suspension adjustments are made, including adjustments to correct any wheel alignment value. Start by installing the quick clamps and wheel sensors onto the vehicle. This is very important. The wheel sensors will have to be moved to the opposite corners of the vehicle, left front to right rear, and right front to left rear. Here's why. The Distronic works with the vehicle at a 0-degree thrust angle. By turning the steering wheel with the sensors reversed, the alignment console thinks the rear wheels are being steered. So turn the steering wheel until the alignment console displays 0 degrees for the thrust angle. Then lock the steering wheel in place. Leave the quick clamps in place and install the headlamp aiming calibration rods. Roll the headlamp aimer to the center of the vehicle and align the beam adjuster with the calibration rods. This special Distronic adjusting tool is required to align the sensor. Using the spacer pins, mount the tool onto the adjuster and attach it firmly with the vacuum pump. Attach the security chain as a precaution. Now you must align the headlamp beam adjuster so the calibration rods are straight on the mirrors. The headlamp range should be set to 0. The laser beam dot should be centered in the reticule. If it's not, the Distronic unit can be adjusted much like a headlamp. There are 3 adjusting screws.